Well, hello, everybody. My name is Mike Beck. I'm with Rhythm Engineering, and I'm the RAM for the area. I've got about 35, 40 years experience in the traffic signal industry, specifically traffic signal. Doesn't mean anything. It just says that, hey, I've got some background and I probably understand your problems. I probably identify with them, and at least you have a sounding board you can talk to about what you're trying to solve. So before we get started, if maybe you could go through and just give me a little introduction as to who you are and why you're here, and how you think we might be able to help you. And then we would go from there. Really, today we're here to talk about optimizing traffic signal operation. And what does that mean? Local problems are just simply, or really just an indication of global problems. We have emissions. We pump 115 billion pounds of emissions into the Earth's atmosphere on a daily basis. That's just, a yearly basis. That's an amazing amount of emissions. And why do we have that? Well, unnecessary stops, unnecessary delays. Here we have a car stop, and you can just see the emissions pouring out of it. Sometimes we have incidents happen on the road, accidents. If it's in a corridor, that just jacks everything up. And again, unnecessary stops, unnecessary delays, primarily due to red light operation. There's also a safety and frustration level here. When people become frustrated, as this woman in the right-hand corner is doing right now, sometimes they take irrational actions. They jump around people, they speed up, they get impatient. There are 30 to 40,000 deaths per year on our roadway infrastructure. That's kind of an amazing number when you figure out that warrants are what we use as a means to justify having an intersection. And the warrants is based on an accident. So we're still having a lot of accidents, and 40% of those accidents happen at intersections. That's, again, very conflicting. So we have a situation due to poor optimization, due to a high level of frustration, due to unnecessary stops and unnecessary delays. We're just fighting each other. So this all contributes to motorist frustration. In 2012, the NTOC got together and decided to come up with a report card on the operation of traffic signals. And what they found was they gave it a grade of D+. I don't know about you, but when I went to school, you had to work really hard at doing nothing to get a D+. And it's the same thing here. 70 to 90% of all intersections haven't even been retimed in as much as maybe 5 to 10 years since their deployment. Well, isn't traffic a living, breathing organism? Doesn't it change? And if you're not going to change the parameters of your controller, if it doesn't have a baseline to move from, then you're going to have poor optimization. They also found a lot of intersections don't even have communication. In today's world, that's just not acceptable. Between modems, between Wi-Fi, between satellites, between wireless communications, there is no reason not to have adequate communications to those intersections other than line of sight. But obviously, line of sight isn't the only reason. So what do we have here? This is kind of a metaphoric picture to basically say to you, this is a traffic engineer, and this is what they're doing today. They have staff reductions because of cutbacks in revenue from taxes and assessments. They have other responsibilities other than just traffic signals. They don't have enough time to get the job done. They don't have enough resources, and they don't have enough money. If you have coordination in your city, whether it's TOD or possibly some legacy adaptive, you're going to be getting one of two phone calls, and this is probably what he's answering. I'm on hold. A guy calling up saying, hey, there's nobody around, and I'm sitting here doing nothing. And you have to explain to them that, well, you're probably on hold. We're waiting for that platoon of traffic to come through. As soon as it does, you'll get to go. Well, that doesn't make any sense to them. Or you might get the phone call, I pulled up, I know this intersection, you skipped me. And it happens all the time. And then you got to try to explain to a person who doesn't know traffic what transition is. Transition is the process by which a controller actually can skip a phase because we did something in it that allowed it to do that. Not a great situation, but it's there in most of our legacy systems. So kind of a hard time explaining all that, and it makes your job very, very tough. So in comes Reggie Chandra. He's the founder of Rhythm Engineering. He found that given his best efforts, his best work, he still didn't have the tools to get the job done. He has a mission statement. He formed the company in 2008, and his mission statement is simply one thing: bring our loved ones to their destinations safer and faster. But remember, and look at that, safer is in there. Safer and faster. It's not just a statement, it's a proven fact. NSYNC is the most widely deployed optimization or adaptive type process in the United States. We have 2,700 intersections under our control. That's more than all others combined. I was having a discussion with David Gamboa the other day at Caltrans at a retirement party, and he said, "Mike, what are you doing now?" I said, "Well, I'm working for Rhythm Engineering. I'm involved in adaptive processes." He goes, "Adaptive? I'm here. They're being pulled out. It doesn't work." I said, "You know, Dave, you're right. In most cases, the system doesn't work. It can't get the job done. Your hands are tied." Not so with our product. 50% of other systems have been turned off since 1970. That's how long Adaptive's been around. Only 1% of our systems have been turned off. Now, we started in 2008. Others started in 1970. We have more than anybody else. We have better performance, better metrics, and less people unhappy or turn off the system. Why is that? Because we do it different. We are an optimization. So let's talk about our impact and what exactly that means. I'm going to skip through this slide so we don't have to listen to Jim. But essentially, Jim Dickinson was one of our first customers. And he has a particular situation where the city swells from 70,000 people that live there to 130,000 people in the daytime. That's a major impact. He also has a major retail outlet. Hold on. Major retail outlet. He has unpredictable traffic because of that major retail outlet. He started with just 5 intersections. Now 75% of his intersections are under our control. That's a very happy customer. This particular deployment here is what I call a 12 by 12. You'll notice that the red dots are in front of that town center mall that he was talking about. It's a major retail space. There are interstates around. There's 2 major interstates around this area. He has seasonal, unpredictable traffic. He does have a TOD, but it's unpredictable. The TODs just can't handle that type of traffic movement. There's occasional saturation. He has intersections that are crossing arterials. We were able to provide him with a 24% reduction in delays and a 56% reduction in stops. That's amazing numbers. He's expanded, like I said, to 75% or 87 intersections in total in his city under NSYNC control. This is a very satisfied customer, but it's also a fairly large customer. So let's look at a smaller job. This is 2 intersections on the 202 in Pennsylvania. Again, it happens to be in front of a major retail outlet, the King of Prussia, the largest mall in the country. But for travel time, within those 2 intersections, before NSYNC, it was 1 minute and 45 seconds to get through those 2 intersections. After NSYNC was turned on, it dropped down to 1 minute and 10, a 33% reduction in travel delays, 20% reduction in stops. Again, we got the job done. It was only 2 intersections. However, those 2 intersections turned into a very happy customer. We now have over 450 intersections in PDOT. Let's talk about even maybe a smaller deployment, different reasons. This is the city of Santa Monica. When I first started my career in traffic signals, it was for the city of Santa Monica, one of my very first customers. I know them intimately. They are a park-driven quality of life town. Here, they used CMAQ to get funding to deal with emissions from people coming through their town, not even living there, and polluting the air with their cars. They found that after NSYNC was deployed, they saved over 100 gallons per day of fuel being consumed. 29,000 gallons a year. That's Monday through Friday, not even talking about weekends. There was a 38% reduction in emissions in this half mile. That's just over 5 intersections and a half mile. Those are great numbers. Now, we're going to talk about San Diego a little bit. And again, given my experience, I know San Diego, when a new technology comes in or a new application comes in, they look for the worst example that they can give you to test it. They don't want to give you something that can be done. They want to give you something they fear can't be done. And this is one of the worst examples of congestions that we've had at Rhythm Engineering. It stretches from Highway 5, you can see here, all the way over to the ocean. Now, this is the college town. Now, what happens at a college town when the sun comes out? That's right, everybody goes to the beach. Well, they felt that if we could give them bidirectional platoon management, progression, and we could cut down on some of the delay, we better balance the traffic operations on this and give them what they needed. Let me show you what we actually provided. This is before and after. What was a 48% reduction in delays from the travel, a 44% reduction in stops. Now, this is both eastbound on the AM, but even the minor improvement would be the westbound and the PM. You can see that we still did a really, really good job at making an improvement across the board. Average speed, same thing. Travel time reductions, exact same thing. So how do we know this is working from a casual observation? Google, and you may not know this, but your cell phones trigger the Google Maps with regards to the red or the yellow. You can see it before and after here on this slide. The red is prior to our install. You see a bunch of red there on the left-hand side. On the right-hand side, it's all gone. Same time frame, same days, it's all gone. It's gone from red to just a little bit of congestion. That's not us saying it. That's not an engineer saying it. That's Google saying it from people on the road. Another example of metrics would be VDOT. Here's a great example of a major study that was done to understand just what optimization could do for you. This is the 5-year study, 3 years before deployment and 2 years after. And what VDOT found over 151 intersections, 13 corridors, combined, they found a 67% decrease in stops. I mean, that's almost like not stopping at all. A 36% decrease in travel time. That's significant. A 58% increase in average speed. Again, not speeding, but because you're not stopping, there's no delays, there's no frustration. Everybody goes a little bit faster. But bigger than that, remember that statement in the mission statement about safety? They found a 17% reduction in total crashes collectively. That's an amazing number. I don't know anybody else that's even come close to advertising that. This is verified proof done by VDOT. But let's talk about the economics of this decision. They found for every dollar invested, they got back to the constituents $8.92. Isn't that your job? Isn't that our job to save our constituents money and time? So some of these numbers you're seeing are not only from us, which we will give you befores and afters, but we like for you to have independent evaluations. We think that it's a better means of you being able to rely on those numbers, not letting the fox tell you what's going on. So FDOT, VDOT, and PDOT all have significant deployments. 450 or more intersections in their states. Very happy with our system. They have those metrics, and they've been able to prove performance. But if you're not a DOT that doesn't have those types of resources, there are many, many engineers throughout the nation that understand this process, understand travel time, and can give you accurate representation of before and after. We highly suggest that you do that. Now, once you know us and trust us and there's a relationship, you may pass on that. You may pass on just because of our reputation now, but we suggest that you do that. Here's an impact map, if you will. Now, this is when I started with the company back in October of last year. We had 2,500 intersections at that point in time under our control. We now have 2,700 intersections. The green was deployments, actually in the field. The orange was to be deployed. Again, the Los Angeles, the San Diego, Mountain View deployments have already happened. And so the map is a little inaccurate, but it just speaks to growth. So how does this work? What allows us to have the metrics that we have and the performance we have and the happy customers we have? What has allowed us to have 2,700 intersections under our control and only been doing this for, 10 years? Where everybody else has been doing it for 40 years. Again, it's true optimization. We have this bucket called adaptive, and everybody gets thrown into it. Well, we do that for funding, but we're not really just adaptive. We do it differently. Let me try to explain that. We have three basic idealisms that we fall into or we chop this process into. One is analog to digital. We're going to take that information that's out there and we're going to create it in a digital state so that it can be used real time with real-time action, not looking back action or post-action. We have the local optimizer. The local optimizer is basically just that standalone intersection. And then we have the global optimizer. Well, the object is to get people across a large corridor, right? 2 or more intersections. That's your plan. So the global optimizer is all those intersections connected into a corridor. So what is the first step? Digital, analog to digital. Well, on the left-hand side here of this screen, you're going to see the analog controller. That's what was out in the field 20, 30, 40 years ago. Some sort of cycle timer, split cycle timer. And reality is that controller on the right-hand side, now the latest and greatest, state-of-the-art, whether it's Conolite, Nasdaq, or Siemens, really is nothing more than that analog controller. It does the same exact thing, has the same restrictions. You may be able to store 200 or more timing patterns, but you're really just complicating the problem every time you issue a timing pattern. But that's what it is. It allows you to maybe do it remotely, make changes remotely, and that's really necessary. But the function is no different than the analog controller. That's why we call it the electromechanical control emulator. So we're going to talk a little bit now about what we mean by analog. Some of us may remember, I know I'm old enough to remember sitting in front of the TV and your dad say, hey, we're on channel 3, go put it on channel 11. You had to get up, walk over, turn the dial step by step to get to 11. Well, we don't do that anymore. But that's an analog process. You're going from one point to another through multiple steps. Another description of adaptive with intuitive process would be 1920 in Detroit. This was actually the very first adaptive signal in the country. In the middle of that intersection is a kiosk. And inside that kiosk is a traffic cop. And they have Mylar, red and green Mylar, that they put in front of a candle or a light to tell the traffic what to do. But that traffic cop is there live, real time, can see traffic coming, can make intuitive, smart decisions. What needs to go next? Who's been waiting the longest? This is what the Fed said in 1993 needed to happen. I mean, they put millions, hundreds of millions of dollars out there for adaptive systems, and they're being turned off because they weren't doing it right. They weren't reacting to queue assessment and real-time delay calculations. This cop could do that. Intuitive, smart decisions based upon real-time traffic, real-time actions, real-time data. Let's jump back a little bit. Let's look at the analog process and now the after instinct process. This is the comparison. You can all get your teeth around this and feel this. Turning a dial, hitting 500 and hit enter. That's the difference in speed. That's the difference in decisions. That's the difference in real-time actions. That's what we're talking about. We don't take data and look at it and every 15 minutes decide what to do about the last 15 minutes. We're doing it right now within the cycle. So how do we get this done? What allows us machine that act decisions based on real-time data and real-time actions? It's not a black box. It's a state-of-the-art machine that allows us to do things intuitively, quickly, real-time. I'm going to show you something here that basically is just what we all know in the traffic signal industry is a ring and barrier. We have 8 phases. We're going to run those 8 phases, 1 through 4 on the top, 5 through 8 on the bottom, and make sure that we don't have conflicts and that this is the order in which we will step through. That analog process, phase 1, 2, 3, 4, phase 5, 6, 7, 8 simultaneously, but it's an analog process. I have to do these state pairs in this order. That's the ring and barrier. And you're going to see it sort of perform here. We all understand this if you've been in traffic for any period of time. What we said was we should have a way with today's technology to basically rename it. Call it a pair state by a digital name. Then if we need to serve A1, we serve A1. If we have no demand for A2, we might be able to go right to C5. Well, that's a smart decision if you have no demand. Now, some people will talk about driver expectation. We're going to cover that in a bit, but this is smart. Your job as a traffic engineer is to move traffic and do it as quickly and as smartly and as intuitively as you can, like that traffic cop. Right? The controllers cannot do that. And anytime adaptive resides on a controller, it has the same restrictions. It can't move traffic as efficiently as it needs to be done. So, that all being the case, let's talk a little bit about failure mitigation, because that's really important. So I've told you basically how we do. We're going to get into the nuts and bolts in a bit, but what if something went wrong with our system? What if it broke? This is not a perfect world. Things happen. So we have plug and play technology as far as vision and detection. We have optimization. We have a pick a state, an intelligent way, release it to the controller, and bam. It does. If something went wrong, the controller just takes off and goes off like it was before. Right? And we'll cover that in more depth again. The local optimizer, that's the next step. This is kind of bringing some of those things together. What is the local optimizer? That's that standalone intersection. I'm sorry there's a little green flag there across the top. I wish it wasn't there, but this kind of shows you what we do. We're looking at an approach, and we're looking all the way down the approach. And we can see as far as the camera can see. And then what we do is we segment that approach, and we can actually tell how many vehicles by numbers are actually in that approach. And we also know when they got there. So we have a delay time, and we can measure that. What did Einstein say? If you can't measure it, you can't improve it. But when you can measure it, the conclusion is you can improve it. We needed a technology that allowed us to measure it. And that's one of the things that Reggie developed and patented in 2008. So let's put it in maybe different language for you. We're going to call this the greedy algorithm. This is going to oversimplify what we do, but it's going to try to explain to you how we look at and how we come up with the metric of making decisions. Let's pretend that you're a traffic cop and you have a roll of gold coins. And what you're going to do, you're going to hand out a gold coin to every time a vehicle stops and waits. And every 5 seconds they're there, you're going to give them another gold coin. Well, pretty soon, you're going to run out of gold coins. You're going to want to get them back, right? So you can hand them out to somebody else. This sort of oversimplifies our thinking, our algorithms, and our process, but it's a good way to get your teeth around it. Here we go. So you can see that on the right-hand side, that's the mainline progression. They're both going now. Your left turns and side streets are starting to build up. They're on the on the left-hand side. And you're going to see the left-hand side start to get higher in numbers than the right-hand side left turns or side streets. Well, when it comes time to gap out and do something, the computer can then say, wait a minute, I'm going to go to where we really need to go. And he serves that side street. Or he serves a left turn. But it needs to get done.
I don't see anything connected.
So here we are again at that same ring and barrier digital state that we started to come up with, and we're going to show you another way of explaining this. Let's say this time I needed 18 seconds because I know how many people were there precisely, and I can put a number to that I need to run. I don't have to run min or max. I can run it for 18 seconds. And then I don't need to go to C5. I need to go to C2. And I need to give it 22 seconds. I'm able to do that because I have real-time information that allows me to make real-time adjustments of the moment, of the second, of the cycling. But then I don't need to go serve C3 because there's no traffic, so I can move on. That's the local optimizer. So let's talk about the ultimate plan, and that is the ultimate goal, and that is to get the global, the corridor connected and working together. What we're going to do is we're going to schedule mainline progression, but a little bit differently than most systems. We're going to give bidirectional mainline progression. And then when the mainline's not running in both directions, we're going to use that period of time for side street and left turn optimization. That's what we're trying to do. That makes sense. So we guarantee green time based upon calculations. We're able to adjust that, but we're going to get those platoons and green tunnels through, and we're going to serve all other phases during the non-coordinated, unscheduled time. That makes sense. Let's put it in another way of saying it. Let's do it with a calendar like you do on your phone. Everybody's used to calendars, right? So we're going to schedule, again, mainline progression in both directions. We're going to replicate that based upon demand, historical demand, numbers and counts. We're going to plan that. And then we're going to create our offsets and do multiple intersections, 10, 20, 30, 3, 2, doesn't matter. There's going to be an offset that's going to allow us to replicate that plan based upon actual numbers that are there. And you can see they're all a little bit different. But let's say in this period of time, or what you would know as cycle, this is what we're going to measure our period of time or cycle to, that this is what we're going to use for optimization of side street and left turns, right? That's pretty common sense. But what if we needed immediately more time and didn't have enough time available to us in that particular cycle, that particular period of time? We can dynamically change the period of time without transition to the entire system. That's a huge benefit to you. Basically, we're saying you're going to get back maybe 30% of that time that you wouldn't have in other systems because it's in transition. We do it dynamically. We virtually eliminate transition, except for possibly an emergency preempt. So we have now more time. This is now our gray area, but we can do one more thing. What if we needed to grow the westbound, but shrink the eastbound time? That gives us more time to deal with side street and left turn mitigation. Here's kind of an engineering way of looking at it. This is your green band that you typically all understand and know with traffic signal optimization and planning. That's what you typically would have on your report, but we have, remember, bidirectional at the same time. You don't have a morning plan and an evening plan. This is both at the same time. And the black boxes or the black square boxes represent, again, the time you're going to use for optimization of side street and left turns. And we touched briefly on failure mitigation. I want to go into a little bit more detail now. What if you had a processor failure in the field, our smart digital box? Well, we just simply fall back to controller operation. You've had time to look at our numbers, massage it, think maybe I should tweak my TOD to be in line with this for fallback, and you can certainly do that. But worst case is you're back to where you were before. It's not any worse than that. What if we had a camera go down? Well, we have something very unique in our process. We look at let's say it happened at 4:05 on a Friday afternoon. We go back and look at the last 4 Fridays at 4:05, and we run that timing as an average. That's probably pretty accurate. Now, I wouldn't try to do that over a long period of time, but it gives you an opportunity to get the camera fixed. Oh, and by the way, you do get an alert, you do know that it's down. So this allows you to run the intersection pretty doggone close to what would be needed anyhow. Pretty historical, or is giving you current times, and get through the process. But what if you lost coordination? One of the things we do in our system is we are distributed. You don't come back to a server. So you haven't got that complications of communication issues. Everything happens at the cabinet in the field. But if you lost coordination between cabinets, you simply would go to local optimization at the cabinet that doesn't have communication. It's that simple. So how is NSYNC different? I've told you a little bit about some of the things we do. Pictorially, what do we do differently? It boils down to our detection system that Reggie invented, patented, that allows him to do things differently, allows him to do things the way that the feds said needed to be done in the 90s. Second generation adaptive systems, which was coined by Urban Systems in San Diego, basically said, look, most legacy systems use spot detection, minimal information to make major decisions. It's not accurate, it's not complete, and it's spot detection. So this picture kind of shows here's a whole intersection in gray, but we're using these little white areas to make the decision of what to do. Obviously, there's a lot more going on, there's a lot more need going on, a lot more changes going on than in the gray than we're allowing to be represented to the controller. NSYNC does it differently, quite differently, actually. You couldn't afford to put that much detection out in the street. Not only that, but your controller couldn't handle the input channels when the amount of detection is here. More detection, more information, better decisions. Pretty simple. So again, now traffic is coming through. We're getting more information through the entire approach. And if we look at this based upon the gray area and white area that we compared to it last time, you'll see that we're looking at the entire intersection to make a decision. We're not looking at spot detection. So to kind of sum it up, an operation, what is the difference between responsive or adaptive versus real-time adaptive operations? This shows where we're responding to a need in traffic. We have a pre-planned operation. This is what you're going to be able to do. It's not flexible. It's not dynamic, but these are the steps you're going to take to operate traffic under legacy systems. I have a demand here where I needed more time. You can see it in the darker color. Hopefully it shows up on your screen there. But I don't have the ability to adjust it. I don't have the ability to do it within that period of time, within that cycle. So best case, absolute best case of most systems, they just do it the next cycle. Well, wait a minute. Well, is there not their next cycle? Well, it's the same thing in an iteration of time. An iteration of time is maybe 10 minutes or 15 minutes, and you're making decisions based upon 10, 15 minutes ago, how are you going to run now? That's why they call it iteration of time. It's not accurate. It's not ideal. It's not real. Wouldn't it be nice to have real-time data like everybody does, but take real-time actions like we do? That's the big difference. So they apply it the next cycle, run that movement. What do? We make immediate adaptation to both the mainline progressions of real counts. We are able to run the necessary time for the side street and left turns, provided there is enough period of time to do it. We make immediate adjustments to the maybe decreased demand for side street and left turns. It's a living, breathing, it changes. Right? But we know what it is because we have QSS. So within the period of time, within the cycle, we can normally make changes that will handle real-time demand, real-time actions, real-time traffic. And then we can also say, wait a minute, that queue is not the same. It's far less for some reason or far greater for some reason. We can now schedule that real time. We're watching your traffic second by second, minute by minute, in constant communication with our detection systems and our processors, combined as a team to make immediate action for your traffic efficiency, optimization, and flow. So in a nutshell, that's what makes us big picture, top down different. So how do you manage all this? It'd be nice to have a set of tools that allows us to manage the system ourselves if we so want to. By the way, we can be your partner. We can do all this for you. We have 24/7 support. We have a team of engineers that are around the clock to help you for emergency calls or just assistance, reports, whatever the case might be. But wouldn't it be nice to do it on your own? If you have the time and the resources, you certainly can. In-Traffic is our central command system. Now, we came out with a new version 1.6, and we released it about 3 months ago. And with 1.6 was the In-Traffic module. It allows for you to manage the system on any device that you might have in your infrastructure with your employees. OS, PC, Android, makes no difference. Access anywhere with security at any time. We also have the ability to collect, synthesize, and give you reports based on what you're specifically looking for, what you're trying to get out at that particular moment, what information you need because someone asked you a question. We can do what ifs. Wouldn't it be nice to say, hey, you know, what if I did this? What if I tried this? What would happen? And you can do that with our system. Intuitive drag and click. Now, this used to be something unique that only a few special companies had because of the cost of development, but everybody has it now, just about everybody. It's really a necessary tool. It's how we learn in school. It's how we practice in real life when it comes to scientific computations and algorithms and expectations. We have the ability to view all the approaches on one screen. Now, folks, there's a lot of information here, but if you take the top left-hand screen, you look on the right quadrant, it says 72 seconds to start. Obviously, that number would be changing if this wasn't a still shot. That tells you when mainline progression is going to start. It says eastbound left turn to westbound left turn is going to start at 2345 and run to 2400. So again, you know what is going to happen by watching it in advance on your system. You can see where there's detection. You can see what phases are green and red. Everything you need to understand what's going on at the intersection live is available to you through our web UI. That's great. We have the Inform module that allows you to collect that data and to massage it and give you reports, do it in graph form, detail form. Again, you have all the tools to make intelligent decisions that are now becoming part and parcel to a system with ITS. You're not missing anything by not going with somebody else. We have it all. So what is rhythm engineering? We want to be your team. We want to give you complete support. We want to do the best job available today at optimization. We want to bring technology into the fold. We want to allow our intersections to operate without constraints. We want to efficiently handle traffic volumes. We want to efficiently handle side street. I mean, let's face it, you got two side streets parallel to each other. You got one sitting with 3 cars, and you got one sitting with 12 cars. Now, the ring and barrier would say the 3 cars go first. Logically, that's not a great decision. Don't you want to get as many cars moving as you can at one time, as soon as you can, to get vehicles through? Yes. So let's talk about that driver expectation thing. When's the last time you got in a car and expected to stop? And if driver expectation really was an issue, why would we be able to prove a 17% safety factor and reduction of accidents? It would be just the opposite. If driver expectation was true and it was a negative result, we would have different results. We'd have poorer performance. We would have more accidents. Our system works and works really well. Glenn Bollinger of Augusta, Georgia, basically said it's like having several extra traffic engineers on staff. I don't know about you, but given the staff resources and cutbacks and money, wouldn't that be nice to have someone you can just get on the phone and talk to? If you're under warranty with us, it's free. You never have another penny to pay. Rhythm Engineering wants to be your partner. Justin Hall of Virginia says, hey, everything we have heard and seen about InSync is positive. We don't get very many calls. We get less calls, which typically means, hey, we're running better than what we were before. Chaz DeVitas, remember that story I told you about PennDOT, 2 intersections to 450? Chaz DeVitas is the signal supervisor for PDOT, and he's a very, very happy customer. Anytime I call, they are available to guide you and to help you step by step. Linda says, hey, not only does it work, but we're a lot safer. I'm not exactly sure what she proof that. All that combined, what does this mean?
Mike,
You do not feel that partnership. Yes.
Can you go back to about Linda Voss? It was kind of cutting out for a second.
Oh, sorry.
No, it's quite all right. It was the internet connection's poor.
Okay.
So sorry to break up the flow.
Oh, no problem. Linda Voss of Topeka, Kansas says, the number of stops is way down, and it's a lot safer. That's not just speculation. We have proof. We have reports that show that, remember, 17% safer with our operation. 5-year study, 3 before, 2 years after. Again, the numbers aren't speculative. They're not ambiguous. We can prove the safety factor. Let's say we become partners. We put a system in. Here's our promise to you as a partner. With up to 3 months of adaptive operation, you do not feel our partnership has had a positive impact in terms of reduced travel times, emissions, fuel consumptions, and improved safety, we will give you 100% full refund of our product. Who else offers that? I know of a system that was installed in a competitor, was installed in Roseville, finely tuned TOD corridor. They found negligible difference because of that legacy technology. After 3 months, they got those 2 phone calls we're talking about being on hold and being skipped because of that process, and turned it off. It cost them $75,000 for those 2 intersections. They wasted their money. So in summary, why the differences? Why consider us? Well, in legacy systems, there's transition. 30%, up to 30% of your time can be wasted just getting in sync with each other, in step with each other. They are fixed cycles. They're not dynamic. They are fixed sequences. To change a sequence, you have to send out another timing pattern, which means transition. They have ring-based limitations, and they operate off of time-of-day plans. Why? Because they're on the controller. It's the only way they can change operation. It's the only way they can react after it's happened. Our system has real-time demand inputs, but also real-time adjustments, immediate adaptation, immediate optimization. We have dynamic sequencing. Now, you can reduce that if you want, but why would you? We can certainly say, no, we're not going to be as dynamic as we want to be. But again, why would you? You want to move traffic. That's your job. We have bi-directional progression, and we're flexible for changes in demand. You have a plan, the plan's not there, the numbers aren't there, we can be flexible enough to adjust our numbers to meet the real-time demand, whether it's less or more, immediately. So what are our next steps? How can we help you? Is there a corridor we can look at? Do we need to have more discussions? How can I be your partner and show you the benefits of our systems and what we can do for you? Thank you for your time.
All right. Fantastic, Mike. Thank you very much.